I should point out that I was the manager of advanced statistical research for Bio-Rad Laboratories, but I officially retired a little over a year ago. However, Bio-Rad has been kind enough to ask me to continue to work on a part-time basis, giving talks like I am here today in Barcelona. So thank you, Bio-Rad, for bringing me to Barcelona. And I continue to work and help them with developing software solutions and education materials related to quality control. Now today I want to talk about linking QC performance to patient risk. Now laboratory risk management is an area that has received a lot of attention in recent years, and there are a number of guidelines that have been published relating to risk management in the laboratory. Here are three that are particularly relevant. You might be familiar with all of them. There's ISO 15189. There's another ISO document, ISO 14971, and then a CLSI document, EP23, titled Laboratory Quality Control Based on Risk Management, which has influenced a lot of the work that I will be presenting to you today. Now, in these risk management guidelines, patient risk is defined as the combination of the probability of occurrence of patient harm and the severity of the patient harm. So it has two components: probability of occurrence of patient harm and the severity of that harm. In the EP23 guideline, they provide a very nice model showing an example of the sequence of events that lead from an initiating cause of an out-of-control condition, ultimately resulting in patient harm. So a nice model relating the probability of occurrence of patient harm from an out-of-control condition. Each event in the sequence has some probability of occurring, denoted by the letters P1 through P6. So some initiating cause leads to a testing process failure. When that testing process failure occurs, depending upon its magnitude, it leads to an increase in incorrect results being generated. And then depending upon the laboratory's quality control procedures and practices, there will be some expected number of incorrect results that are reported before that out-of-control condition is detected. When the laboratory reports an incorrect result for a patient, it creates a hazardous situation for that patient. And whether or not that hazardous situation leads ultimately to patient harm will depend upon the likelihood that an incorrect result is acted upon inappropriately. So while this is a very nice model, the authors of the guideline, I think for purposes of ease of use and simplicity, recommended that rather than try to estimate these probabilities, that instead that the laboratory simply categorize the probability of occurrence of patient harm into one of 5 different categories. Both CLSI EP23 and ISO 14971 give examples of those 5 categories in their meaning, shown here. For EP23, the categories are given as rates in time. So frequent means once a week. Improbable means once in the lifetime of the measuring system. Alternatively, ISO 14971 gives these rates in terms of harmed patients per number of reported patient results, so a proportion of reported patient results. So frequent means greater than 1 harmed patient for every 1,000 reported patient results. Improbable means less than 1 harmed patient for every 1 million reported results. Likewise, both ISO 14971 and CLSI EP23 recommend that severity of harm be categorized or classified into 5 categories. And both documents give the same definitions for those 5 categories. So negligible means inconvenience or temporary discomfort to the patient, all the way down to catastrophic, meaning patient death. Once the laboratory has made an assessment of the probability of occurrence of harm and the severity of harm for a particular measurement procedure, then a risk acceptability matrix is used to determine what is an acceptable risk to the patient. The general idea here being that the more severe the harm to the patient, the lower the probability of occurrence of harm must be in order to be acceptable. So, for instance, if the assessment is made that for this particular measurement procedure for this patient population that the severity of harm would be serious, then the risk acceptability matrix here would say that the probability of harm can be no greater than occasional in order to be acceptable. So, to summarize, patient risk is defined as the probability of occurrence of harm and the severity of that harm. And while EP23 provides a very nice model of the sequence of events that lead to patient harm, they recommend replacing that model with this simple one-step model that just categorizes or classifies the probability of harm from an initiating cause of an out-of-control condition into one of 5 categories, from frequent to improbable. Thereby, in doing this, removing all of those middle steps where laboratory quality control plays a role. That all went away. So if we want to try to link what we do in quality control in the laboratory to the patient, we have to do better than this one-step simple model. It's not going to help us much. So I'm going to spend the rest of my time revisiting this model and talking to you about the ways that we might be able to quantify these different steps in the model and come up with a quantitative prediction for the probability of harm. Well, the first thing we need to do, which I've skipped over, is define what we mean by an incorrect result. Now, clearly, all patient results that we report contain measurement error. They all contain measurement error. So how do we define what we mean by an erroneous patient result? Well, there is a CLSI document, C24, which is on principles and definitions for quality control for quantitative measurement processes. The 4th edition was recently published. I happen to be the chair of the committee that wrote this 4th edition. And the committee came up with this definition for an erroneous result, which is borrowed from similar definitions that appear in other guidelines. So a patient result that fails its quality requirement. So an erroneous result is a patient result that fails its quality requirement. So what's the quality requirement? Note 1, the quality requirement is usually expressed in terms of an allowable total error. If the measurement error in a patient's result exceeds that allowable total error, the result is considered erroneous. So this is where quality specifications come in. This is where we define the quality requirements for our test results. Now, the committee chose to use the term erroneous result. Notice in the figure that I showed you from EP23, they call it an incorrect result. Likewise, some of the early literature in this stuff published by myself, I use the term unacceptable result. So note 2 here states that erroneous result may also be referred to as an incorrect result or an unacceptable result. I'll try to use the term erroneous result in this presentation, but if I say incorrect result or unacceptable result, it means the same thing. A patient result that contains measurement error that exceeds the allowable total error specification. Okay, so we've defined what we mean by an incorrect result now. So let's kind of go through these sequence of events. First, we have to think about what is the probability of producing an erroneous result when the process is operating in its stable, in-control state. Hopefully that probability is very, very low, and this is really kind of related to the sigma value of the method. We can compute the probability of producing an erroneous result when a process is operating in its in-control state by knowing the imprecision and bias of the method and the allowable total error specification. We then need to think about how frequently our measurement procedure incurs test system failures. How often does it go out of control? This is really reflecting the reliability of the measurement procedure. This is the thing that instrument manufacturers focus a lot of their time and effort on, making reliable instrumentation. And typically we would quantify or think about reliability in terms of something like mean time between failures. How often or how frequently do we experience out of control, true out of control conditions in our measurement procedure? So we can quantify that, or we can at least have an assessment of that. Now, when an out of control condition occurs, depending upon its magnitude, that will determine the increased likelihood of producing results that fail the quality requirement. And I'll just give some cartoons to kind of explain that. So this is meant to show the distribution of measurement errors for a measurement procedure. We're assuming here that the measurement procedure is unbiased, so this distribution is centered on 0, and the spread in the distribution reflects the imprecision, the stable imprecision of the process. On the bottom are listed TEA plus and minus. That's our quality specification. It turns out in this case, the quality specification happens to be exactly at plus or minus 3 analytic standard deviations. So this would be called a 3 sigma process. When our process is operating in this in-control state, the way that we would determine the likelihood of producing an erroneous result would be to measure the area under this curve that's to the left of negative TEA and to the right of positive TEA, which is actually shaded in green in this figure, although there's so little of it you might not be able to see it. It turns out that there is about a 3 in 1,000 chance of exceeding the quality requirement if you're operating a 3 sigma process. So that's the way we would compute the probability of producing erroneous results for the in-control state. Now, what if an out-of-control condition occurred and it caused this measurement procedure to shift upward so that this was the distribution of measurement errors while we're in the out-of-control state? While we're producing and reporting results in this state, there's a little over a 15% chance of producing results that have measurement error that exceed the quality specification. A larger error would have even a higher likelihood of producing erroneous results. So in order to study the impact of our QC processes, we need to study a wide range of possible magnitudes of out-of-control condition that might occur. Now, when erroneous results are reported, or when an out-of-control condition occurs, how long it manifests before we detect it will be a function of our QC procedures and practices. So to give you an idea of how quality control relates to the number of erroneous results that might get reported in the event of an out-of-control condition, I'm going to go through a quick example using some simulated data. So this is an example of a glucose measurement procedure. From left to right, we're going in time, okay? The black dots in that upper figure represent patient results, and the diamonds represent QC results. So in this particular case, a pair of QCs are being tested approximately every 50 glucose measurements, okay? The bottom panel is showing the measurement error in each of those results in the upper panel. Now, in truth, we don't know the measurement error in our results, so I have simulated these measurement errors. I've simulated them based upon an assumption that the CV for this method was 2.5%. So based on a CV of 2.5%, I generated random measurement errors for each of those results in the upper panel. Now, in this particular case, I'm going to assume that the allowable total error specification for this glucose measurement procedure is plus or minus 10%. Those are denoted by the dashed yellow lines in the lower figure. I'm also going to assume that the laboratory is using a QC multi-rule, a 13S22SR4S rule. So now, let's assume that at some point in time, an out-of-control condition occurs. At that point in time, I simulated a 5% shift downward in the results. So all the patient results from that point on are 5% lower than they would have been otherwise. Now notice in the upper panel, it would be very, very difficult to discern that a 5% shift downward had occurred because there's so much biological variability in the patient results. It's easy to see in the lower panel, in the measurement errors. Of course, remember, we don't know the measurement errors in the patient results. We only know the measurement error in the QC results, which is why QC results are so effective in detecting these kinds of problems. Now, at the next set of QCs that are tested after this out-of-control condition occurred, we get two results that don't fail our quality control rule. So from our perspective in the laboratory, everything looks okay. So we continue to produce results and report them. At the next QC event, we get a rule rejection. Both of those results are more than 2 standard deviations below their target value. So in this particular case, there were 89 patient results that were affected by that out-of-control condition. All 89 of those are 5% lower than they otherwise would have been if that out-of-control condition hadn't occurred. But of those 89, only 3 of them contain measurement error that exceeds the quality requirement of plus or minus 10%. They're denoted with yellow dots in this figure. Now again, we don't know which of those, we don't know how many and which ones it would be because we don't know the measurement errors. All we know are the reported results in the top figure. The only way we would know if we had 3 or more would be to shut down the process, correct the problem, repeat all these patient results, and compare the original result to the new result. But we know it here because I've simulated it. Now, of those 3 erroneous results, notice that one of them occurred since that last accepted QC event, and 2 of them occurred prior to the last accepted QC event. The distinction here is that I'm going to make the assumption that if it was an erroneous result that was reported prior to the last accepted QC event, it's a final result that creates a hazardous situation for the patient. But if it was an erroneous result that had been reported since the last accepted QC event, I'm going to assume that that result was either never reported or that the laboratory has the ability to identify those results and correct them before they're acted upon inappropriately. So I'll refer to those as correctable results. Now, I just showed one particular simulation of a 5% shift downward in the testing process. Of course, if I were to simulate that again, I would expect to get different numbers in terms of the number of QC events it took to detect the problem, the number of patient samples affected, the number of those affected patient samples that were erroneous, final, or correctable. So let's assume that I repeat that simulation of a 5% shift downward 10,000 times. And for each of those 10,000 simulations, I record the number of events it took, the number of QC events it took to detect the problem, the number of affected patient samples, and the number of erroneous results, final and correctable. And if I do that, I can generate frequency distributions, which are shown here. The upper left panel is the number of QC events to detection. The upper right panel is the number of patient results affected. The lower left is the number of erroneous final results, and the lower right is the number of erroneous correctable results. And if we compute the average of those distributions, those are parameters that are of interest to me. And I've denoted them here with the notation that I use in my work to represent them. Of particular importance to us in this talk will be ANPED. That's the average of the distribution in the upper right panel, the average number of patient results affected by the out-of-control condition, and ENUF, which I refer to as enough, which is the expected number, the average number of erroneous results reported that are final, that create hazardous situations for the patient. Now again, we've done this just for one particular out-of-control condition, a 5% shift downward, but we really need to ask the same question for a wide range of possible out-of-control conditions. And if you do that, you can generate curves. So this is the curve for ANPED, the average number of patient results affected. The horizontal axis is the magnitude of the out-of-control condition, given here as a systematic shift in the process in percent, ranging from minus 20% shift downward to a positive 20% shift upward. And the vertical axis is the average number of patient samples to error detection. The little red circle is the one example that we just went through, the 5% shift downward. Now this curve is not generated by doing simulations. That would take too long. This curve is generated mathematically. I developed the mathematics to allow us to compute this directly. The little red dot was that simulation to kind of make the case that the mathematics is predicting what the simulation would show. This is the curve for the expected number of unreliable or erroneous final results. Okay. And again, the 5% shift downward is shown. Turns out the 5% shift downward is about the worst case here in terms of the expected number of erroneous final results. Okay, so I'm trying to make the case here that we can compute, based on the magnitude of an out-of-control condition, the expected number of erroneous results that we expect would be reported before we detect the out-of-control condition. Now lastly, depending upon this measurement procedure, the analyte, and how it's used in patient care, there's going to be some likelihood that an erroneous result that we report gets acted upon inappropriately. Some analytes contain very little information that's used in making decisions. In that case, the probability of an erroneous result leading to an inappropriate decision or action might be low. In other cases, the analyte is a critical component of the information that's used to make decisions in a patient. In that case, the likelihood of an erroneous result leading to an inappropriate decision or action might be very high. Now, I want to emphasize that here we're only thinking about what is the likelihood that an erroneous result leads to an inappropriate decision or action, independent of the severity of harm to the patient from that action. They're separate concepts, okay? So now we've gone through this entire sequence of events, and I've tried to make the case that we have the ability to estimate something about each of these sequences of events. And if I give them notation, this is the notation I'm using for each of those. And with a little bit of advanced math, you can combine all of that into an equation for the predicted probability of harm. Notice it's a function of SC, the magnitude of the out-of-control condition. Now, I don't expect you to understand how that was derived. I would never expect you to calculate it on your own. What you should be able to expect is that software tools would be available that would do that for you. All you have to do is provide the inputs, and this stuff gets computed. Now, let's consider defining what I'll call a risk management index. The risk management index will be the predicted probability of harm, the thing we just talked about, a way of being able to compute, divided by the acceptable probability of harm. And the acceptable probability of harm that we'll use will be based upon the assessed severity of harm and a risk acceptability matrix. So if we compute an RMI by computing the acceptable probability of harm from the severity and the predicted probability of harm based on our assessment of reliability, the quality control strategy, and the likelihood that an erroneous result leads to an inappropriate decision or action, and get this RMI, what we're looking for is that the RMI be less than or equal to 1. If the RMI is less than or equal to 1, that means that the predicted probability of harm is less than or equal to the accepted probability of harm, therefore acceptable risk. So I'm going to use this and go through one example of how we might consider using this to relate a quality control strategy to a predicted probability of harm or patient risk. So I'm going to use the same example that I gave before for a glucose measurement procedure with a CV of 2.5%, the allowable total error being 10%. I'm going to assume that in this situation that about 100 patients per day are being tested for this method, and the laboratory has determined that the mean days between test system failures is about 30 days. On average, about once a month they get a failure, an out-of-control condition. So we can compute the mean number of patients between failures as 100 times 30, or 3,000. Their QC strategy is 2 QC levels, evaluated once per day using a 1-3S rule. The assessment has been made that the probability of harm given an incorrect result, the probability of making an inappropriate decision or action if a measurement error exceeds the allowable total error is about 0.5, which is about one out of every 2. And the assessment's been made that the severity of harm when an inappropriate decision or action is made is minor. I don't want to quibble about whether those make sense, so that's just for this example. So a minor severity means, if we use the ISO 14971 risk acceptability matrix, that the probability of harm can be no greater than occasional. And if we look at the definition of occasional for ISO 14971, it means that we have to have less than 1 harmed patient per 10,000 test results. So, taking that information, our definition of RMI is predicted probability of harm divided by acceptable probability of harm, and our acceptable probability of harm is 1 in 10,000. So this is what we're going to do. We're going to compute predicted probability of harm, divide by 1 in 10,000 to get our RMI. Now, if we use the simple model proposed by EP23, how do we decide whether or not our QC strategy, what its predicted probability of harm is? We have to pick one of 5 categories. How are we going to do that? We guess our opinion, our best opinion, or do we just pick the category that assures that our probability of harm is acceptable? I don't know. Well, what if we use this model? Now, I've provided all the information we need to compute this predicted probability of harm. And if we do that, we get a figure that looks like this. So the curve is the curve for the predicted probability of harm as a function of the magnitude of the out-of-control condition. That curve. That dashed blue line is the average of that curve over the range of out-of-control conditions that are being considered here. The red dotted line is the acceptable probability of harm. That's 1 in 10,000. The ratio of that blue dashed line to the red dotted line is the RMI. So in this particular case, our predicted probability of harm is about 2.56 times the acceptable probability of harm. So we would conclude that our risk is 2.5 times greater than we would like it to be. So, what can we do? Well, let's consider changing the QC rule. We'll do a more powerful rule. So we'll change from a 1-3S rule to a multi-rule. If we make that change, what do we do here? Did that change in the rule change us from probable to occasional, or occasional to remote? Or what if we apply our predictive probability of harm model. This is what we had for the 1-3S rule. This is what we get for the multi-rule. So the predictive probability of harm due to an out-of-control condition has been reduced, and the average now has been reduced, but the average is still 1.5 times the acceptable. So we've improved, but not enough. So what else could we do? Well, we were evaluating QCs once a day. What if we evaluated QCs twice a day, every 12 hours? What impact would that have? Does it change? How do we know? If we compute the predicted probability of harm using the more robust model, this is what we had for once per day. If we change to twice per day, it goes to this. So now the average is 0.95, or the ratio of the average to the acceptable is 0.95. So now we have an RMI that's less than 1. Our risk is about 95% of what we consider acceptable. Okay. So in summary, a lab's tolerance for reporting erroneous patient results should depend upon the likelihood that erroneous results lead to harm and the severity of the harm. The lab's impact on patient risk is going to depend upon the in-control performance of the lab's measurement procedures, the sigma metric, the reliability of the lab's measurement procedures, how often does it fail, and the lab's QC strategy. It's important to be able to objectively assess the impact of a lab's QC strategy on patient risk, not just make a guess or give an informed opinion or pick the category that assures that my risk is acceptable. One way of linking QC performance to patient risk is to compute an RMI by computing the predicted probability of harm and dividing by the acceptable probability of harm, and seeking QC strategies where the RMI is less than 1. And again, I wouldn't expect you to be able to compute an RMI, but with my assistance, Bio-Rad has developed software, it's called Mission Control, that can make all these computations. So this is just a tool you should be able to use just like you'd use a chemistry analyzer to get information that helps you, instead of diagnosing a patient's situation, diagnosing your quality control strategy. So with that, I thank you very much for your attention, and we'll move on to the next phase.